In this video, I'd like to talk about the idea of partial derivatives of a function of several independent variables. These are going to provide an analog for the derivative in the Calculus 1 case. It might be worthwhile to review what that was about briefly. In Calculus 1, you had the graph of some function y equal f of x. You select some particular spot on that graph having x-coordinate c and therefore y-coordinate f of c, and you'd like to find a straight line that resembles the graph if you're close to x equals c. The idea that you used was, since I need 2 points to tell me a straight line, I'll think of having another point on the graph. Its x-coordinate will be c plus some number delta x. Its y-coordinate will be the function evaluated at c plus delta x. Since I have 2 points on the line, I can now calculate the slope of that line. It's simply the change in the y-coordinate divided by the corresponding change in the x-coordinate. Of course, this isn't exactly right because this is not in the same direction as the curve right at x equals c. So the thought is I'll take such secant lines and I'll take the limit of their slopes as delta x approaches 0. That corresponds to letting this point slide to the left and approach x equals c. This point slides down the curve, causing the secant line to look more and more like the desired tangent line. You made up a symbol for this limit. You called it f prime at c, or dy dx at x equals c, or a number of other notations. Traditionally, they made you work 1 or 2 examples using the limit definition. Then you developed a bag of tricks that let you do derivatives quickly and easily, and most people immediately thereafter forget that this is where the idea came from in the first place. We need to know this because of what's about to happen. If I have a function of 2 variables, f of x and y, at some spot a, b, I might have a function value. If I want to know the rate of change of the function at a, b, I'm in kind of a difficult situation. There's lots of directions that I could travel in. Therefore, we're going to single out 2 spatial directions and hope that this would be enough to tell us the rate of change in any other direction we might be interested in. I'm going to imagine traveling through the point AB in the positive x direction, meaning that I'm going to change the x-coordinate by a small amount, delta x, but I am not going to change the y-coordinate at all. The distance between the 2 points that I've marked is just delta x. I'm going to write down a difference of 2 function values at nearby points, one of which being the point that I'm interested in. Then I'm going to divide by how far apart the 2 points are, and this will approximately be the rate of change in this direction. This corresponds to the slope of the secant line from Calculus 1. In the first semester calculus, we then took the limit as the distance between the 2 points on the x-axis tended to 0 and called that the derivative. We'll do the same here. I could just say that this is the rate of change of my function in the positive x direction at the point x equal a, y equal b, but going around saying that all the time becomes cumbersome. Therefore, we'll introduce a notation that is similar to what we did in Calc 1, except to make the distinction between functions of 1 variable and functions of 2, we'll alter the notation slightly. We will write a curly d and pronounce this as the partial derivative of f with respect to x at point AB. Just as in Calculus 1, there are a number of alternative notations. People often write the function with the variable that we are differentiating with respect to, and then the point at which we are evaluating such a thing. Of course, you can travel through this point AB in any number of different directions. Another choice would be to travel through the point in the positive y direction. In this case, I'm going to have my nearby point having the same x-coordinate as the point of interest, but this time I'll alter the y-coordinate. The vertical distance between these 2 points is the difference between b plus delta y and b, which is just delta y. Arguing just as before, take the difference of the 2 function values, evaluated at nearby points, one of which is the point of interest, divide by how far apart the points are, delta y in this case, and take the limit as the distance between the 2 points tends to 0. We will have as a symbol the partial derivative of f with respect to y evaluated at AB, or we might write f with a subscript of y to indicate what's the variable now, evaluated at AB. Just as in the first semester, it's traditional to mentally torture ourselves by doing some of these by hand, and then immediately forget all that and begin developing a bag of tricks to easily calculate these things. Likewise, let's let f of x and y equal x squared times y cubed and calculate the 2 partial derivatives of f at the indicated spot. Don't worry, we won't be doing too much of this. We take the limit as delta x tends to 0 of a difference of 2 nearby function values divided by how much the input changed. Since we're doing the partial with respect to x, the y is treated as though it's a constant. We are evaluating at x equal 2, y equal 1, so I subtract away f at that point. I subtract it away from f at some x value, comma, the y value, which didn't change. The x value is going to be a plus delta x. In this case, that would be 2 plus delta x. Also, the way that we do the f procedure in this particular problem is we take the number in the first position and square it. We take the number in the second position, cube it, and multiply those together. So this function value is going to be 2 plus delta x squared multiplied by 1 cubed. In what follows, it's ordinary algebra. Not talking my way through the algebra for brevity, the partial derivative of f with respect to x at the point 2, 1 is equal to 4. What this means is, if I am at the point 2, 1, and I think about the rate of change of the function as I allow the x to increase, but the y has to be constant, then the rate of change of the function value is 4 units of function value per unit of x. This is the instantaneous rate of change. In a similar way, if I want to look at the partial of f with respect to y at the point 2, 1, this time I'm going to leave the x fixed at its value of 2 and let the y vary a little. This time, x is 2 in both function values, y is one thing or the other. F of x squared y cubed is 2 squared times 1 cubed. F of 2 comma 1 plus delta y is 2 squared times the cube of 1 plus delta y. This will work out in a similar way to the other one, but the algebra is going to be slightly messier. Doing the algebra, factoring a delta y out on top and canceling it with the 1 on the bottom, we have to find the limit as the number delta y tends to 0 of 12 plus 12 times delta y plus 4 times delta y squared. The limit of those last two quantities are both 0, and the limit of a constant like 12 is just the constant. Starting at the point 2, 1 and traveling in the positive y direction, the function is increasing at a rate of 12 units of function value per unit of y. If I wanted to calculate a general formula for this partial of f with respect to x, I'd have to calculate this limit. There'd be a fair amount of messy algebra, but if we wanted to, we could do the calculation. In this limit, I'm looking at various function values. The x is allowed to vary from whatever its initial value to x plus delta x, while the y, since it isn't changing, could be treated as a constant. You could do the same for partial of f with respect to y, and obviously in this case, the algebra is going to be considerably worse than it was in the first one. And then a moment of sanity appears to us. I've got this function, f of x and y. It depends on x squared and y cubed being multiplied together. When we're calculating things like this, we are holding the y-coordinate still and moving the x. I could do this. I could use my ordinary calculus rules with the thought in my head that x is the variable, and I'm pretending that y is a constant. In this one, I'm going to hold the x constant and think of the y as being the variable. This is going to take a little bit of getting used to, but when we finally do get used to it, this will allow us to calculate partial derivatives of things like this very easily. So I'm going to go back and think about my function f of x and y equals x squared y cubed. I'm going to form the partial derivative of f with respect to y and partial of f with respect to x. In this context, I'm thinking of x as being the variable and y as being a constant. That means that y cubed is a constant too, and what I'm taking the derivative of is the square of the variable multiplied by the constant in this context, y cubed. When I have a constant factor within a derivative, I can bring it out. But on the other hand, if x is the variable, then the derivative of x squared is 2 times x. This will be interesting. The Mac died in the middle of my sentence. Anyway, this will be interesting. The Mac died right in the middle of my sentence. But anyway, we'll see how this goes. In an exactly similar way, we can deal with the partial of f with respect to y. In this context, I'm pretending that x is being held at a constant value and y is the variable. This means that x squared is a constant factor of what I'm taking the derivative of. If y is the variable, the derivative of y cubed is 3 times y squared, so this partial derivative is easy to figure out. Now, notice I don't say 3 times x squared times y squared times dy dx like we might do in Calc 1. Here, x and y are completely independent variables. Y here is not a function of x or vice versa. This almost seems too easy. Let's do a sanity check. If I evaluate the partial of f with respect to x at the point where x is 2 and y is 1, I'll have 2 times 2 times 1 cubed, which gives me 4. Go back and look at what we did before, and you'll see that that's the answer we got. Partial of f with respect to y at the point where x is 2 and y is 1, 3 times 2 squared times 1 squared, 3 times 4 times 1 gives me 12, and this is the result that we got previously. I want to make this video short. We've introduced this notion of partial derivative. We've seen that calculating them by hand is kind of a pain. We're beginning to see that all of the tricks we learned back in the first semester of calculus are still on the table. So in the next video, what I want to do is I want to look at a lot more examples of how you calculate these things, and I want to think just a little bit visually about what these things actually mean to us. Until then, I hope everybody's having a good day, and I'll talk to you again soon.